Hello friends, in today's class we are going to see one way of evaluation of dependency graph through topological sorting. Hello everyone, and the next topic here in this case is topological sorting. Okay, so dependency graph we have seen, and this topic explain the further the evaluation order of dependency graph. Okay, so this topic is somewhat in sequence of dependency graph, how dependency graph is evaluated. So definition, I already told you that two nodes, in terms of two nodes and semantic rules, if there is a dependency, then A is dependent on B, so B should be evaluated first. Similarly here, a topological sort, okay, the topological sort, the short term is there, of a directed acyclic graph is any ordering, okay, a directed acyclic graph is any ordering M1, M2, Mk of nodes. Okay, so the first thing is important term is we have to find ordering. Okay, ordering of nodes such that edge go from nodes earlier in the ordering to the later nodes. Okay, edge goes from the nodes earlier in the ordering to the later ones. So if I say that A and B, then there will be an edge A to B, there will be an edge. Okay, and if I say A, B, C is the ordering, then I can say that A, there is an edge to B, and I can also say that there is an edge for C also. And B to C, there will be an edge. Okay, that is if Mi is Mj, then an edge from Mi to Mj, then Mi appears before Mj in the ordering. Okay, so that is a simple definition of ordering of nodes, and we have to respect the dependency, this dependency in this case. Now, to just explain you the example here, I have taken consider this graph, and it says that consider the following directed graph. Okay, now we have to find a topological ordering. Okay, we have to find topological ordering for this. Okay, so is it unique? Answer is no. Okay, topological orderings are not unique. Okay, so topological orderings are not unique. So now I can take A, and then I can go for, okay, the ordering I have to say edges are not important. So A, and then I can go for B, and B or D. Okay, so the topological sorting is can do this ordering, and what does it say is that if there is an edge A to B and B to D, okay, so definitely find a edge, find a node that does not have any incoming edge. Okay, so the first rule is find a node does not have any incoming edge. Okay, and remove it and put in the ordering. Okay, so now here we will take A, and then we will remove that node and put that in the ordering. So with that effect, I can say that this edge is gone and this edge is gone. Then I have an option of B or D. Okay, because this edge is gone, both does not have any incoming edge. Then I can go for here I can go for B or D, any one. Okay, because both does not have any incoming edge. Suppose I go for B and I remove this one. Then I can go forward, then I can go either C or D. Suppose I choose D. So if I take D, then this edge is also removed. Then I'm left with A and C, C and E, sorry. So anyone. So that is C, and then I can say finally E, and then finally I can say F. So this is one of the topological ordering. Okay, so this is one of the topological ordering, and you can say that A, and then I have removed this, no incoming edge, B or D. So I choose B, and then I choose D. D is removed, then C and E was there, and C and E, I have taken the order as C. I can't take F because there is a dependency, so C, E, F. This is one of the ordering. This question says that the number of different topological orderings of the vertices in the vertices of the graph is. Okay, so how many different ways we can do this ordering? Okay, so now I can take this example. Let me just take out this part. Okay, so I will solve it here only. How many different orderings are possible? Okay, so now I'll do the same thing. That I will take I'll take an edge here. Let's say vertex A, incoming edge, and then I have option of B or C, B or D. As is removed, so B or D. So I can go for either B or I can go for the ordering as D. Suppose I go for B, okay, then there is option C or D. So I can go for C and I can go for D. Suppose I take C out of it, that A and B and then C, then I have only this path is there, D, E and F. So that is one ordering, D, E and F. But suppose I say this path A, B and D, A, B and D I path take, then there is a choice of C or E. Okay, so here I'll get a choice, that is C or E. If I take C, the ordering here left is E and then F. If I take E, then the ordering left here is C and F. If I go for D, then I have an option. If I A and D, then I have option of B and E. So I'll write here B and E. And if I go for B, then I have a choice of C or E like the previous one. So there is a choice of C or E. If I go for C, then I have a choice only EF. So EF. If I go for E, then I have a choice of only CF. Finally, say if I go for E, A, D, and then I go for E, then I have only this path remains, and that is B and C and F. So B and then C and then finally F. Okay, so this is the different ordering. You can still verify that how it has been done. And the number of total topological ordering, the number of different topological ordering is 6. Okay, so that is how this dependency graphs are evaluated, and this is a simple question of understanding the dependency graph. So that's all for this discussion. Thank you.